Good evening, everybody. Welcome to our International Physics webinar. Today it's our 265th International Physics webinar, and we have with us here Dr. Andreas Hinzmann, a group leader, University of Hamburg, Germany. He is already connected with us. So I'd like to welcome our speaker. Sir, good evening and good afternoon to your part. Thanks for joining with us, and thanks for accepting our invitation, sir. I think it's a good opportunity for a student to interact directly with you. So dear students and viewers, I think you have already come to know the title of the today's International Physics webinar. Title is The Searches for Physics Beyond the Standard Model at the LHC. So I think you will enjoy it, and you can also join with us using the link. I will send the link in the comment section, and you can also ask question by commenting in the comment section. So sir, you can start your session.
Okay. Yeah, thank you very much for inviting me to the webinar. It's a pleasure for me to give you some insight into searches for physics beyond the standard model at the LHC, and I will try to give you a rough overview of the topic and then give you some recent results from the last year in this field of physics. Okay, so let me start with the standard model of particle physics. So by now we have a very clear picture of microscopic interactions of elementary particles and how matter is composed. And this is all summarized in a pretty small model of these particles shown here and described by a quantum field theory that can, if you want, fit on a cup. So we have a very well description of the electromagnetics, it's weak and the strong force to describe matter. And this has all only been possible with collider experiments, and most important particles in the standard model have all been discovered at collider experiments. Just a few highlights from the recent years. So Petra discovered direct evidence for like a gluon, which is a force-carrying particle for the strong force, and the Z boson at SPS, and the top quark, which is the heaviest matter particle in nature at the tevatron. And then recently, the Higgs boson finally discovered at the LHC, the last missing piece of this picture right here. And it's already a 10th anniversary this year of the Higgs boson. While this Higgs boson was certainly the main goal of LHC, there is a whole program to search for beyond standard model physics, and that is what I would like to describe to you today. Okay, so yeah, why is that model not the end of the story? And that's because we have many open questions left in particle physics that are not really addressed by the standard model of particle physics. And the first questions you can imagine when you just look at this picture. So why do we have 3 generations of matter? And why do they behave the same? Why are there not 4 or less? And why do the particles have these patterns of masses that somehow arise? We don't know exactly what is the type of particle for neutrinos. They can be Dirac or Mariana particles. And we have in total 26 parameters that we need to measure and are not predicted by the standard model itself. So it's not a theory of everything with just one parameter yet. Also we have only 3 of the 4 important forces in nature described. So gravity is described by general relativity and not included in the standard model. So naturally the question arises, can you unify all of these forces in a single unified theory? And there's also a large hierarchy between the gravitational force and the standard model forces that I'll talk a bit more on the next slide. But before that, these are problems that just arise from looking at the model and the beauty of it. But when you go, there is also evidence from astrophysical observations that the standard model doesn't describe everything in nature. And the 2 most striking ones are dark matter. We have many observations that lead us to believe that there must be dark matter in the universe that we don't know what it is, but we know that there's 5 times more of it than the matter that is composed from standard model particles. So clearly, understanding what is dark matter is physics that we would like to understand, and that can also be addressed with collider searches at the LHC by looking for new particles that could be these dark matter particles. And another observation is that our universe is composed of mostly matter and not antimatter. And naturally, if you think of just a Big Bang where you start from energy, you would expect equal amount of matter and antimatter. And the standard model itself doesn't have enough mechanisms to describe differences between interactions for matter and antimatter. So some extra beyond standard model physics is needed to explain that. Yeah, and then also from ground-based experiments, we have observations that do not match with the expectation from standard model. And one example is a recent measurement, again, from the muon magnetic moment that is measured recently also at Fermilab with extremely high precision and can also be predicted by the standard model with very high precision. And still we observe a 4.2 sigma, so more than 99.99% probable disagreement of theory and observation in experiment. So there's clearly a mystery of why the standard model prediction does not work here. And then we have also at the LHCb experiment several observations that show differences between the different flavors of charged leptons, so muon and tau. They are not equally produced in some decays of B mesons, and that is not described by the standard model, so it's clearly a mystery, and these are the so-called flavor anomalies that motivate beyond standard model physics explanations. Yeah, and I already said I want to point out one more problem a bit more because it's a good way to demonstrate the different kind of ideas that we have to address problems, and that is a hierarchy problem. So if you think of the gravitational force and say electromagnetic force in daily life, they seem to be of similar strengths. Imagine a magnet and an apple. That is almost the same strength you could imagine, but the difference is quite large, in fact, because for the nail, this is a 6-gram object, but on the others, for gravitational force, this is a force between 6 times 10 to the 29 grams of particles. So you need much more particles to get the same amount of force. And that, in other words, if you consider elementary particles, so single particles, the gravitational force is many orders of magnitudes weaker than the standard model forces. Yeah, and that leads to a problem when you want to think of the evolution of the universe with just these two models and basically try to predict the history of interactions since the Big Bang all by the standard model. That means you want to have it valid all the way until the scale of where gravitational and standard model forces become equal. And that is when you reach very small interaction distances, so small radii, then the gravitational force becomes equally strong, and that is at very high energies. And this energy is an energy that only appeared at the very shortly after the Big Bang. It's order of 10 to the 19 GeV. Yeah, so the wish is that we have the standard model valid up to the order of 29 GeV to explain basically everything that happened since Big Bang. But this is actually a problem with the standard model theory because it's a quantum field theory. Some quantum fluctuations like in this diagram can happen. So a Higgs boson can produce a TT bar pair and then go back to a Higgs boson. Such that when we go to very high energy, say the beginning of the universe, and we see the Higgs boson mass becomes corrections of this type of order of the Planck scale. Yeah, and with that theory, if we want to, with that theory to predict nowadays Higgs mass to be 125 GeV at very low energies, well, then the mass value must be extremely fine-tuned such that the initial mass and these corrections cancel to give us exactly 125 GeV as we observe in experiments. So it's a highly unnatural scenario to have such a low Higgs mass if this theory is supposed to be valid up to very high energy scales. Yeah, and there are many ideas how to solve this and also the other problems beyond standard model theories. And here I give you 3 examples. And these all tackle this hierarchy problem. And the 3 main ideas here are, so these kind of diagrams are responsible for the corrections, but how about if the Higgs boson were not an elementary particle, but actually a composite particle? So thinking that our current elementary particles are not the smallest elements of nature, but they are even smaller particles that interact with some new force and bounce them together to something like a Higgs boson bound state. Yeah, and by introducing such a new compositeness, new force, this hierarchy problem is circumvented. Another idea is to introduce so-called supersymmetry. That introduces a new symmetry in the theory that means that we have for every particle in the standard model another super partner with similar quantum numbers, except that every fermion becomes a boson and the other way around. And these theories then predict a top quark partner, and it has the property that this diagram and the one up here, they cancel each other. So the hierarchy problem is somewhat circumvented. And the other rather big idea is to introduce extra dimensions. So we have 3 dimensions of space that we live in and believe the forces can act in, but you could also imagine there's another extra dimension that is small and curled up such that you don't see it. And if you let gravity propagate into that extra dimension, but not the other forces, then gravity could appear much weaker than the other forces and effectively explain this hierarchy between gravity and the standard model forces. So what effectively happens is that this Planck scale is much reduced such that everything can be described easily. Yeah, these are 3 ideas. There are certainly much more ideas and models beyond the standard model. But what they all have in common, I mean, they can solve multiple of these problems, and they also have candidates for new forces or new matter that we should be able to see in high energy interactions. So at the Large Hadron Collider, for example, we should be able to produce new particles or see new interactions that we did not expect from the standard model itself. Yeah, and that brings me to the Large Hadron Collider. So this is a machine that we built a couple of years ago. It's running already since 2010. We have here a ring of 30 kilometers underground and border of Switzerland and France, and collide protons, 2 protons that at a very high kinetic energies. So we can have collision energies of 7 to 14 TeV. And that means the particles hit each other with such a high speed that we can probe interactions at very small scales of order 10 to the minus 19 meter between quarks, between quarks and the protons. So what in fact happens is that we not just the whole protons collide, but individual quarks are kicked out of the protons and interact. Yeah, and in this collider, we have 4 experiments at 4 interaction points. The 2 biggest one are CMS and Atlas. They are composed large detectors that They are basically built to reconstruct any possible particle that is produced in proton-proton collisions. And here I show you one example. This is a CMS detector. So you see it's built like an onion shell around the interaction point with multiple layers of tracking detectors and calorimeters, and measure the tracks and the momenta of all of the particles being produced, such that from these pictures we can calculate back what happened in the interactions. Just to give you some scale, it's 80 million channels, so comparable to a digital camera, but we have 1 billion collisions per second. So this is way faster than any camera you can think of. And we record 300 of these 80 million bit pictures every second on hard disk and analyze them. Yeah, and I told you already it's running since 2010, and since then we have collected a large amount of data. The last run was a so-called run 2 from 2015 to 2019. And here we collided protons at a center of mass energy of 13 TeV and recorded the so-called integrated luminosity of 139 inverse femtobarn. This integrated luminosity tells how many interactions of a certain probability we would see in the experiment. So the number of observed events is the luminosity times the cross-section, or the probability for a certain particle interaction process. Yeah, and since 2019, we've been in a long shutdown to repair and upgrade our detectors and also the Large Hadron Collider. And in the following years, we plan to operate the LHC again for 3 to 4 years at a bit higher energy, collecting yet more data, and then upgrade yet one more time up to 2029 and collect yet 10 times more data in another decade. And the more data we collect, the more rare processes we can actually test with the LHC. And before I start with an actual search, let me just briefly tell you how we could see new interactions of force carriers at the LHC. So in the standard model, we describe interactions, say, for example, the electromagnetic interaction, by the exchange of force-carrying particles, a photon, for example. So what we would see at the LHC is, first of all, from the standard model prediction, typically we have processes like the one on the left, and those rapidly fall as a function of the invariant mass or the energy of this interaction system. So highly energetic interactions, or hitting full with full energy to quarks, is less probable than just a low energy interaction. If we had a new force-carrying particle, like the Z boson, for example, and this energy of this particle the mass of the particle is smaller than the collider energy, we would be able to produce that. So a new force-carrying particle X, I call it here, something like the Z boson, we should be able to produce it at the LHC, and then we can see it as a resonance in this invariant mass spectrum. And this is how we can directly detect new force-carrying particles at the LHC. But this only works if these new particles have masses smaller than the center of mass energy of the LHC. If these new force carriers have higher masses, then we can still see signs of new forces. In this middle region here that I labeled EFT, we should still see that the interactions that are not agreeing with standard model predictions, we could have new interactions I've drawn here, and they are typically labeled contact interactions, anomalous couplings, or effective field theories. They are small. They are small differences from the standard model expectation, and they are first hint of yet a new force-carrying particle at higher energies. And we pursue searches at LHC in both ways, either searching directly new particles with high mass, or just look for small deviations of standard model predictions. Yeah, and let me now summarize what is the reach. So how high of a particle mass can we actually measure at the LHC? And the answer is it's not quite 14 TeV because we're not colliding quarks, but protons with each other. So we need a certain probability to find a high momentum quark inside the proton to let them interact to produce a new particle. And here I've given an example of a heavy new boson interacting with quarks, similar to the Z boson, but heavier mass. That we could observe at the LHC. So this is one of the particles which we can observe at the highest possible masses. And here you can see what mass reaches we can see in run 1. With a luminosity of 20 inverse femtobarn, we could reach up to 3 TeV masses. In run 2, this is almost doubled. So 5 TeV is what we can reach here. And run 3 and HLC, we will go even a bit higher in this mass reach. This is relevant for very high mass particles to look for at the LHC, and you can see that run 2 is certainly a very interesting point because we've have a large jump since run 1, so there's a high potential for new discoveries at this point. Then how about cross-section reach? So how low, how rare of a process can we look for deviations in interactions at the LHC? And that is nicely summarized by this plot here. Here we should see the cross-sections or the probabilities of processes predicted by the standard model that we've measured. So WZ boson production, top production, Higgs production. If you look down to the very lowest cross-section process in this plot, this is the so-called vector boson scattering. That is the last processes that we've looked at. Here we have interaction not just of quarks, but actually of 4 heavy standard model bosons, W and Z bosons, with each other. So here we're really probing interactions only involving weak, electroweak bosons. And we can look for deviations from beyond standard model physics that only couples to the W and Z bosons here. Yeah, and in principle, I put here this dot run 2. This is the lowest possible process cross-section for which we can still observe one event in LHC run 2. So here at the bottom, there could be a lot of beyond standard model physics hiding. And that is what we search for. And the theme of the LHC search program for beyond standard model is really to leave no stone unturned. So we really want to explore any possible idea of BSM scenarios and signatures. And you see here in this picture an overview of searches here at the CMS collaboration. And colors integrate different model ideas, and each row is a signature, and then the exclusions or limits on these models are shown in this plot. Just to give you an idea of how large this program is, we've looked for in order of 100 signatures with full run 2 data already, and another 100 is still ongoing. So what show today is just this snapshot in the middle of the data analysis of run 2. Yeah, and what I focus on to do today is give you a bit of an overview, but mostly focus on a few examples to point out new developments. Okay, and I've ordered the talk like this. So I talk first about searches for new forces or interactions bosons, and then second part, new matter or new fermion particles. And I focus on cyno-exotic signatures today. There is also larger programs for dark matter, SUSY, and long-wave particles I have in the backup in case you want to ask questions about them. But if I focus on a few examples here first. And I've picked one interesting signature that we look at recently, and that is looking for a heavy resonance called X. So that's a new particle decaying to Higgs boson pairs. And Higgs bosons, they decay in more than 50% of the cases. They decay into B quarks. So the signature that we look for here is some new particle resonance. Imagine it like a new force-carrying particle, like the Z boson, decaying to, in the end, 4 quarks, and quarks actually are not observed as single particles in the detector, but they form a whole shower of charged and neutral particles, such that we see 4 jets of particles in the detector that you can see here in this event display. And these jets, we can reconstruct them with so-called jet algorithms to calculate the momentum of these 4 B quarks, roughly, with jet algorithms. And the real challenge here is actually to distinguish such events from standard model background, because the standard model predicts such 4 jet events quite frequently at the LHC. And I've shown you on the bottom left one example diagram. And this is a diagram involving only quantum so QCD or strong interactions. And that is why it's quite high probability, a much higher probability than our signal that we are looking for. So the real challenge here is not to just construct these 4 jets and the invariant mass in order to find the resonance, but to distinguish these from background events. And here the techniques have developed quite a bit in the last couple of years, and I would just like to give you a bit more insight in these techniques, because that is where the development happens. Yeah, and that brings me to so-called boosted boson tagging techniques. And here, so I show you here again the decay of the Higgs boson into B quarks that form these, say, blue jets here. But in this case of a heavy resonance, we're actually in a special scenario, because we may have multiple TeV X resonance, X resonance decaying into Higgs pair. So say we have a 2 TeV resonance decaying into 2 Higgs bosons. So each Higgs bosons can carry an order of a TeV of kinetic energy and be very fast. So it has a large Lorentz boost. And that means in the detector, because the Higgs mass is only 125, so TeV is really large boost, then the decay products from this Higgs jet, they will actually be very close to each other. And if you look at this picture of such a Higgs jet, it's hard to see that there are actually 2 jets inside it, but only like 2 very close to each other calorimeter cell, and then a bundle of charged particles. So you can analyze the substructure. You really have to analyze the structure of this reconstructed jet to be able to distinguish this from a simple quarked or gluon jet from background. Yeah, and the features that you can use here for distinguishing such a jet from background are basically 3 main features. First of all, you know the mass. The Higgs boson jet should have an invariant mass of around 125 GeV. Background should be very small. There should be some substructure, so something like 2 subjets versus 1 subjet. And then we have B quarks inside both of these in this Higgs jet. And B quarks have the special property that they form B hadrons, which have a relatively long lifetime, such that they can fly in our detectors a few millimeters before they decay. And that means we can reconstruct with our tracking detector secondary vertices or decay vertices inside such a Higgs jet. And the techniques here have developed very strongly. So starting from analyzing the shape of such jet to distinguish single axis jet from 2 subjet axis jets with simple observables. Then more recently, we've also looked at really studying the whole energy distribution inside a jet with some picture. And the advantage, if you do that with a picture, then you can use here, this is a quark jet with just with most of the energy in the center and less energy at the edges. While for a Higgs jet, you would have two energy centers in that jet. But by regarding the jets as a picture, you can use standard neural network image recognition techniques to distinguish them and get quite good performance. But we've even gone a step further now, and nowadays we really use all of the reconstructed information from our detectors that we can have. So really use as input to a neural network all the reconstructed particles at up to 100 for a jet, with each of the 42 properties and also all of the vertices, and use all of that information in a graphical neural network. So you have a graph neural network with like a point cloud to really use all the information in an optimal way to distinguish signal from background. And that allows you to, and then now showing this plot here, for a certain signal efficiency, say at 50%, to have a background efficiency of only 10 to the minus 3. So these kind of taggers allow to reject the background by a factor of 1,000 while keeping half of the signal. And this is what we really need to search for such Dihiggs resonances. Yeah, and here's how this search then works. Here an example from the Atlas correlation. So here the search is performed in both topologies. First for lower X masses looking for 4-jet events, and then for higher X masses looking for 2-jet events with substructure. And then for each kind here on the left, these plots, the invariant mass of the 4 jets or 2 jets is calculated, and the green area, that is the standard model background expectation. It's steeply falling. And if there were a new physics resonance, we would see a peak on top of that spectrum, as you can see with these colored lines. But yeah, but then you can compare that to the data. That the black points are the observed collision data, and you don't see any peak in that spectrum. That means we haven't discovered such a resonance yet. But we know we can set a limit on how high could maximally be the cross-section or the probability for such a new physics process. And that is what we then quote on the right. So the black line in this plot here is the highest possible cross-section that is still allowed for a new physics resonance, given this observation here in data. And yeah, the red curve is a theory prediction from one of these extra dimension models predicting actually graviton resonance particles for this X. And we can exclude these in mass ranges from 300 to 2 TeV here in this search. Yeah, so that is basically the result of this search. But I'd like to tell you one more interesting feature that is common to many of the searches that we do for beyond standard model physics. And that has to do with the background estimate. So this green area that I've shown you here is the expectation from standard model. But in fact, since it's QCD multi-jet background, it has this complicated Feynman diagram here. The standard model prediction is actually not very precise. So for this search, we actually do not use only a pure theory calculation to get the standard model prediction, but we use a so-called data-driven technique with a sideband. And there's a quite simple trick for Dihiggs resonances how to do that. Because if you look here in this 2D plot of the reconstructed mass of both of these Higgs bosons jets, they should peak at 125 GeV. So this signal region, so this SR region is where we expect our signal. And this is where we have drawn these Dihiggs invariant mass spectra. But around it, there's a lot of data which has very similar properties to our signal, but doesn't contain it. So it's only background enriched data. So, and that is what we make use of. So really use this control region around the signal region to predict the shape of the background and then extrapolate that to the signal region to predict the background. And then in between, there's a validation region where we can make sure this method actually works. Okay, so that was one example of a search. And just to complete the picture, that was just one search, but we do, of course, look for any possible new force carrying particle. So this X could be anything listed on this slide, and the particles to which it decays can be Higgs bosons, but also any other standard model particle, leptons, neutrinos, quarks, WZ, photon, anything like that. And the resonances could be, for example, spin 1, spin 0 particles, that means extra Higgs bosons. I mean, in the standard model, we have discovered only one spin-zero particle, the Higgs, but the extensions of the standard model, they predict up to 5 typically, and we're looking for other Higgs bosons in such a way. Also, more spin-1 particles like the W and Z could exist in like these composite models that I introduced. Gravitons, I already mentioned. They're also so-called axion-like particles. There are dark matter candidate particles. And finally, leptoquarks are very special particles which have both lepton and quark quantum numbers. So neither quark nor lepton. And if these particles exist, they can do something very interesting. Namely, they can transform in this picture here a B quark into a lepton. So they can change quarks into leptons, and that is a possible explanation for these flavor anomalies that have been observed at LHCb. So searches for leptoquarks are also quite interesting these days. Yeah, and I'm not going to cover much of these examples, but give you 2 more searches for new force carriers with exploring not just the simple resonance as I've discussed before, but more complicated scenarios. And the first one is looking for vector boson fusion di-Higgs production. So here we're not looking for a pair production of Higgs bosons only, but we do it in a channel with vector boson fusion. That means we have 2 vector bosons, so that can be W or Z, coming in and then interacting and producing 2 Higgs bosons. And at the LHC, that means we have a final state with 2 Higgs bosons and 2 quarks. So in the end, there is not just 4 jets in the event, but 6 jets in the event, or 2 jets plus 2 jets with substructure. Yeah, and the standard model predicts multiple ways how these interact. And among the standard model interactions are these 2 diagrams that I show up here. And one diagram involves the coupling of the Higgs to these to a pair of V bosons or WZ bosons. It's called kappa V. And there's another interaction in the standard model where Higgs boson coupled to Higgs boson pairs coupled directly to vector boson pairs. It's called the kappa 2V. Really, the standard model predicts both of them, and they actually cancel each other such that the total cross-section is very small. But if one of these diagrams did not exist, then we would see that because then we would see an excess. And that you can see in the bottom left plot. This is again the di-Higgs invariant mass spectrum, but this time in this VBF vector boson fusion topology. So you have much less events because now we have these 2 extra jets that have to be produced in background. So it's much less probable. And it's again steeply falling in orange for QCD multijet production. But for the signal, and the signal is here a new physics scenario where the second diagram does not exist, but is removed by some mechanism, then we would actually see here an excess of events at the very highest di-Higgs invariant masses. And that allows us really to constrain these 2 coupling parameters. They are in the standard model, we have set them to 1. So at 1, 1 is the standard model expectation. And this curve here, this band in this 2-dimensional plot is the expectation, is the exclusion limit. So the standard model is well within the expectation, but this cross here, that's a scenario where one of these 2 interactions is disabled. That is actually excluded. Yeah, and here, that I give you one more example that is a bit more complex here. Now looking at a completely different scenario. So here we look at signatures where we could find leptoquarks. This S1 is a leptoquark, and I show you how that works. And we make use of the fact that we colliding protons and not antiprotons at the LHC. So we have we're starting with U and D quarks, so first generation quarks, and not antiquarks. And if we have that, then, and we have a leptoquark that couples to quarks, then this U quark, for example, in this diagram up here, can be transformed into an electron, positron, La plus positron. And the opposite interaction, like anti-up to electron, it doesn't happen much at the LHC. So what we would observe at the LHC would be an imbalance of electron and positron observation. So if we measure the ratio of the cross-section of E plus mu minus events or E minus mu plus events, then for standard model, we expect in all interactions that to be 1. But if such a leptoquark would exist, this S1 particle, then we would see a difference. And similarly, in supersymmetry, there are scenarios with other particles that can create such an imbalance in E plus mu minus events. Yeah. And here, this is a new signatures, first time explored at the LHC. We've measured this ratio of E plus mu minus, and it's found to be unity, and then that with multiple jets and missing energy in the signature, just to make sure that we cover as many scenarios as possible with this search. And that allowed actually to, there was no evidence, but we could explore a new piece of leptoquark scenarios that has never been looked at before. So here up to 1.8 eV leptoquarks and some coupling were never explored before. Yeah, that was the end of new forces or new interactions looked for. And the second kind of search I wanted to show you are new fermions. And here there are basically two main ideas of what fermions we could have. I mean, if we look at the standard model, there are 3 generations of matter particles, of fermions. So the natural question is, why don't we have 4 or even more? And with the discovery of the Higgs boson, we know that there cannot be a 4th generation of fermions because these would couple to the Higgs boson, and then it would have completely different couplings measured. So the discovery of the Higgs boson more or less excluded that we have a 4th generation of the same type of matter. But we could have slightly different kind of matter, so-called vector-like quarks. They transform differently under the then the standard model quarks, so their left and right-handed components are the same. So they don't need a Higgs boson to generate them. So they are independent of the Higgs boson, and that's why they can exist even after the discovery of the Higgs boson. And they could be special and interact only with the 3rd generation of matter, and that would help actually, again, with this hierarchy problem where we had this top quark loop part that could be cancelled with such vector-like top quarks. Yeah, and so what we look for is such kind of vector-like quarks, so heavy partners of quarks, and we can produce them at the LHC. And here's just one slide how this search is done. And first thing to recognize is here's the production of a single vector-like quark, this large T. That's a vector-like quark which has a similar properties as the top quark, just is much heavier. And if you look at the decay, I said to 3rd generation quark, so in its decay you have a top quark, and then a Higgs and a Z, and yet maybe another top quark. So up to 9 particles in the final state. And many possibilities of ways how it can decay. So if you really want to search for these, you have to consider all of these possibilities and categorize events according to the number of particles that you observe, of W's, of Z's and Higgs and top and B and so on. And in each of these categories, what is done here is to reconstruct an effective invariant mass of the single vector-like quark in the middle plot here. So that is reconstructed for every category shown on the left. and then use all of that information together to look for excesses in data, and that allows to constrain vector-like quarks and coupling on the right plot up to order of 2 TeV masses. And that's not the end of the story. Vector-like quarks, there's not just one possibility, not just a top partner, but also B partners. They can be also produced in pairs. So you have a large program of such searches to look for vector-like quarks. And in the end, all of them indicate no vector-like quarks up to order of 1 to 2 TeV invariant mass. Yeah, and that was a new quarks. And similarly, one can also think of why are there not more leptons? And there is actually one very good motivation for having new leptons, and that is the so-called heavy neutral leptons or heavy neutral neutrinos. So an extra kind of neutrino, which is much heavier than the neutrinos that we have. And the reason why this is particularly interesting, because they can, in principle, via a seesaw mechanism, somehow like pictured in this plot here, explain why the masses of the neutrinos in the standard model are extremely small compared to the charged lepton masses. So there's a theoretical motivation to have another generation of neutrinos that is much heavier, an order of 100 GeV or TeV, than the neutrinos that we know are super light. Yeah. And since these are very heavy particles, one looks for them really similarly to the previous examples I've shown. Again, here we're looking for a new resonance WRA. This is a new force-carrying particle that can decay into N is the heavy neutral lepton, and then decay further up to 2 quarks and 2 leptons, and then look in this invariant mass for an excess for both this heavy W right, this new force-carrying particle, and the heavy neutral lepton. And then one can explore basically 2-dimensional of space of heavy neutral lepton mass and W right mass. And most interestingly, this is one of the few searches where we do not see perfect agreement of the standard model a description with the data that we observe. So here, if you look at the highest bin in this distribution, you see there's more data than we expect from the background. And the probability for that to still be consistent with the standard model is at below % level. So this is like a 2.7 sigma evidence. But since at the LHC we perform so many searches for beyond standard model physics, this is not enough to claim evidence or discovery of any new particle yet, because just by searching in so many places, we have quite a large probability to have data fluctuating up. And so we only claim really evidence up to, from 5 sigma level. Nevertheless, I think this is one of the interesting examples to follow up in later running of the LHC, where we have more events to even confirm or exclude this kind of new physics sign that we have here. Yeah, that brings me to the summary and conclusions. So we have already a large number of models and signatures explored at the LHC. And key, gave you one example to do that is with new reconstruction and analysis techniques. And they actually help equally as the new data that we are collecting. And I gave you examples of new models and signatures that we've looked at for the very first time with the run-2 data. There were just hints, but no clear evidence for beyond standard model physics yet to report. So we've extended significantly the range of models phase space that we exclude. But still, this is just the middle of it. I've told you that we've analyzed only half of the LHC run-2 data, and there is still a run-3, run-4 to come. So there are still many stones left unturned and many exotic models, signatures, techniques that we haven't even looked at. And the detectors and triggers that we use to record these events, they will even be upgraded for the run-3. So we have yet more signatures that we can look at. Yeah, thank you. That was the end of this presentation. I'm happy to take your questions and discuss with you.
Yeah, thank you, sir, for your wonderful presentation. So we have got few questions. So if you allow, we can start our discussion session. The first question, how they consider they find new particle practically as they are non-reactive to any known force and extremely small half-life. Can you see this question? I have added the question in the screen.
Yeah. Yeah, so I think so the question is about how to find particles that are which have very small coupling or no coupling to the known particles and forces. Yeah, certainly if we look for new physics at the LHC, we can only find them there if they have some way of coupling to the standard model particles. So either they couple to quarks inside the protons that we collide, yes, then we can produce them, or they couple to, say, only the Higgs boson, that's also enough. If you, for example, consider dark matter, we know dark matter is something that exists, and we also know that it should interact extremely weakly with standard model particles. So we know that we should, in principle, be able to see some interaction with the standard model particle. The question whether this interaction is strong enough to be observable at the LHC, that's unclear. Yeah, I mean, we search with the machine that we have, but if the interaction is more rare, or even at higher masses, then that's the limit of the current collider, and that can only be found in future collider experiments.
Thank you, sir. I have another question. So how they place detector at perfect angle to collect interactions of particles?
Yeah, so both the CMS and Atlas detector, they are built exactly around the collision point. And if you have, for example, a new physics particle produced, that's typically produced at rest, so the decay products will fly in every angle with same probability. While standard model interactions typically, T-channel scattering typically tends to scatter more forward, but the detectors are therefore built to capture the whole event. So it's built really in a circle around the around the collision point, and in the center, so 90-degree scattering angle is basically where we have highest sensitivity to new physics resonances, and in the forward region, where there's more background from standard model, or forward and background scattering. But the main the main ideas really cover everything, and there's also yet one more point why we have to measure every particles in every direction, and that is because we also want to be able to measure invisible particles by their missing momentum. So if we had, for example, a dark matter particle that's invisible to our detector produced, we could still see it by summing up momenta of all other particles in the event, and assuming a momentum conservation, we can
thank you.
Measure their momenta. Yeah, exactly. Yeah.
There is another question. So do dark matter really exist, or it's just a miscalculation?
Yeah, that's a good question. And I think by now we have so many different kind of ways how to observe dark matter that I think we are pretty much convinced that it's not a miscalculation. So we have like rotation curves of galaxies, where you need to calculate the distribution of matter within a galaxy. Yeah, you can think, oh, maybe that's miscalculated, but we also have measurements of the microwave background from the beginning of the universe, where from the distribution of this, we can also infer the amount of dark matter that has to have been there to explain the evolution of the universe. We have also gravitational lensing effects. That means we look at stars far away, we can, and there's dark matter in before that star, we would see kind of a lens effect. So by now we really have multiple different ways of being sure that there has to be some dark matter. That I think by now nobody would say it's a miscalculation anymore.
Thank you, sir. We have another question. So why neutrinos do not interact with the Higgs field, and why their masses are so tiny?
Yeah, that's a good question. And I think it's a question that's unresolved. So, I mean, we do know by now that they have some tiny mass because we have seen in neutrino observation experiments some oscillation of neutrinos. So we know they have a very small mass, but this could be generated with the Higgs field, possibly, if they are Dirac particles, but they could also have their masses generated in somewhat different ways. So that's an unresolved question. I think that's the answer. Yeah.
Yeah, thank you, sir. We have another question. So what happened during the collision to electrons exactly at point of time of collision?
Yeah, so I mean, in practice, we're having a proton collider here, so we have protons colliding, but maybe let me answer that for the electron collider, because that's actually simpler. So if we have an electron, and in these collider experiments, we typically would not collide electron and electron, but electron and positron, so a particle and antiparticle. So when they collide, they really absorb each other and can transform into a photon or other boson that can then decay again to other particles in the event. And similar in the proton collider, we're colliding more or less quarks with each other. So if a quark hits an anti-quark, they can annihilate each other and create a new boson particle like a photon or gluon at the LHC. Yeah.
Yes, sir. Thank you. We have another question. So how to join CERN for research?
Yeah, that's also a nice question. Yeah. I think CERN has many programs to get international people involved, and that one is the so-called summer student program, which is typically at the like master level students typically, where you can spend one summer, 3 months more or less at CERN and do a technical project. Doesn't have to be physics analysis, can be anything related to the magnet development or also computing, anything that CERN is doing in order to operate these accelerators. I think this is the way to get in touch with CERN as a student. Also, PhD students positions are offered by CERN, and they have, for more senior people, there are also ways to travel and make a fellowship at the CERN project. Yeah, and even without traveling there, they have master classes to get in touch with scientists at CERN and learn more about what is going on there. And it's really, I mean, CERN itself is not just the particle physics. It's also about the technicalities, engineering, computing, building that is needed to operate this. Yeah.
Thank you, sir. We have another question. So what is the essence of finding new particle at CERN, at LHC?
Well, I try to give you some example what is the most important thing. So I think at the LHC we have, we have already built this collider. So by now, the main essence that we have to work on is to really analyze the data in the best possible way, squeeze out, use the latest techniques like machine learning to best find new physics in this very valuable data set that we've already collected. And prepare possibly for future colliders as well. Yeah, so at the moment we're analyzing the run 2 data, but we're at the same time building the new detector components for an upgrade in 10 years from now to do even more precise measurements.
Yeah, thank you, sir. This may be the last question. Can you send me reference to know about LHC research?
Well, I think the easiest way is to start from the CERN.ch website and explore from there. Yeah, just.
Okay, sir. So thanks again for your wonderful presentation and nice discussion session. It's a very good opportunity for the viewers and the student to learn a lot of things about CERN and LHC and its research. So I think that some of our students and the viewers have already motivated by your lecture, as the main aim of our program to motivate our students. So thanks again for giving us this opportunity to arrange such an important webinar.
Yeah, thank you again for inviting. This was really a pleasure to talk to you about LHC. Thank you.